Okay, so a firm produces output Q using two inputs, labor and capital, with a Cobb-Douglas production function. Q equals L to the power zero point 0.6, K to the power zero point 0.4. Okay, so L is labor, K is capital. So since we've seen the power for labor is greater than the power for capital, so this firm favors labor than capital, or labor is of more importance to the firm than capital. Okay, these exponents, if you were there in our last class when we were looking at these production functions and what these powers mean. So here, this labor is to the power zero point 0.6, capital to the power zero point 0.4. So labor is of more importance. Okay, that's just for your general knowledge there. You won't be asked what they mean. So the wage rate for labor is 200 kwacha per unit, and the rental price of capital is 500 kwacha per unit. The firm wants to produce 1,000 units of output at the minimum cost. Okay, as I said, the production theory, you want to minimize costs and you want to maximize output. All right, so the first question is write down the cost minimization problem for the firm. Okay, so the cost minimization problem, just remember this is the formula. W is the wage rate. W is the wage rate. Okay. L is the number of workers. Okay. L is labor, just represents number of workers. Okay. Plus R, the rate for capital, times K. K is just the quantity of capital. R is the rate of capital. K is the quantity of capital. Okay, colleagues? W, wage rate. L, number of workers, because L is labor, so number of workers. R, rate of capital. K, quantity of capital. Maybe you can think of it as number of machines, basic. K, number of machines or equipment. Okay, colleagues? Yes. So this, you say W times L plus R times K equals C. Okay, this is the cost minimization condition here. Okay, equals C. C is just your cost. Okay, and the total cost. Okay. Yes. So our wage rate has been given to us. The wage rate is 200 kwacha per worker. The rental price of capital, 500 kwacha per unit. So we just substitute here. Okay, so I'm going to say 200 L plus 500 K equals C. Okay, just how I've put it here. All right. We haven't been given the cost. Okay. Then the production function. Okay, remember production function is Q equals L to the power 0.6 K to the power 0.4. So they told us this firm wants to produce 1000 units. So we substitute Q with 1000. Okay, this is our production function. 1000 equals L to the power 0.6 K to the power 0.4. Okay, so how you answer this question, you're going to say the cost minimization problem is you want to minimize your cost. This is your function for the cost, subject to this, subject to Q equals, we already know what our Q is, 1000. So 1000 equals L to the power 0.6 K to the power 0.4. Okay. Yes. Any questions? So that's what you need to do. Okay. When they ask you for this cost minimization problem, okay, cost minimization condition. Okay. You just write this function, this one here, subject to production function. They'll tell you how many units the firm wants to produce. Okay, those are the two things you need to put: this equation here and this production function. Then you get the full marks. All right. Yes. Part B, derive the optimal ratio of labor and capital using the cost minimization condition, where the marginal rate of technical substitution equals the wage rate over the rate of capital. Colleagues, the marginal rate of technical substitution is the trade-off rate. How much labor you need to give up to get capital, or vice versa. How much capital you need to give up to get labor. Okay, colleagues, this marginal rate of technical substitution is the trade-off rate between labor and capital. Just remember it. Trade-off rate between labor and capital. Okay, how much capital you need to give up to get labor, or vice versa. All right. So this marginal rate of technical substitution, all right, MRTS. Where can I do my workings? Okay, yes. The marginal rate of technical substitution is the marginal product of labor over the marginal product of capital. Colleagues, when we say margin, it just means addition. So marginal product of labor is the additional output you get when you hire one more worker. Okay, colleagues, marginal product of labor, the additional output or produce you get when you hire one more worker. Marginal product of capital, additional output when you get one more machine or one more unit of capital. Okay. So this, it means you have to derive this production function here. This Q equals L to the power 0.6 K to the power 0.4. You need to differentiate, partial differentiation, okay, so that you can get MPL and MPK. All right. Yes. So remember this condition, the cost minimization condition, where The trade-off rate between capital and labor is equal to the wages of the workers over the rate of capital. All right. So always remember this. MRTS equals W over R. Okay. MRTS equals W over R. Then MRTS becomes marginal product of labor over marginal product of capital equals the wage rate over the rate of capital. Okay. So we need to get MPL and MPK. This is our production function. Q equals L to the power 0.6 K to the power 0.4. Okay, so we have to partially derive this production function with respect to L and with respect to K. So the marginal product of labor, MPL, is the partial derivative of our production function Q with respect to L. What this just means, colleagues, is when you're deriving this function, where you're deriving this function with respect to L. Okay, that's what it means. Okay, so this is how we derive it. Remember, with deriving using the power rule, since we're deriving L, so you say exponent multiplied by number in front of the letters, which is 1. 0.6 times 1, you get 0.6. Then you subtract a 1 from the exponent. 0.6 minus 1, you get negative 0.4. You have L, L to the power L to the power negative 0.4 K to the power 0.4. Okay, colleagues, that's how we do partial differentiation. Okay. The marginal product of capital MPL, you're going to partially derive the production function with respect to capital. All right, so you are focusing on the K variable. Okay, so if we derive 0.4 times 1 this side, you get 0.4. L to the power 0.6 K to the power. Now this 0.4, remember you subtract 1. 0.4 minus 1, that is negative 0.6. Okay, colleagues, that's how you do it. Right. Yes. So the marginal rate of technical substitution, you're just dividing these two. So you say MRTS, marginal rate of technical substitution, MPL, so you're going to say 0.6 L to the power negative 0.4 K to the power 0.4 over 0.4 L L to the power 0.6 right, K to the power negative 0.6. Okay. Then we can simplify this. 0.6 divided by 0.4, that is 1.5. Okay. 0.6 divided by 1.4, 0.6 divided by 0.4, that is 1.5. Then here, we're going to use indices, laws of indices. Okay. L to the power negative 0.4 divided by L to the power 0.6. So you subtract these indices. You say negative 0.4 minus 0.6. Okay, you say L to the power negative 0.4 minus 0.6. We also do the same thing for K. You're subtracting the exponents. So you're going to say 0.4 minus negative 0.6. So K to the power 0.4 minus negative 0.6. Okay, so we simplify this 1.5 here. Negative 0.4 minus 0.6, that is negative 1. L to the power negative 1. And for K, 0.4 minus negative 0.6. We got this one down. 0.4 minus negative 0.6, you get positive 1. Okay, so you're going to get 1.5. Since this L is to the power negative 1, so it will come at the bottom here. Then this K is to the power 1, so our marginal rate of technical substitution is 1.5 K over L. Okay. Yes. So colleagues, remember, when you're getting the marginal rate of technical substitution, you're just deriving the what's this production function. Okay, you are just deriving the production function. There is a shortcut. Okay, if this differentiation has confused you and you are telling yourself, no, I'm not going to attempt this in an exam, deriving them, there's a simple way you can do it. Okay, like this. You just remember this. Q equals L to the power alpha K to the power beta. K to the power beta. Okay. Then just remember this marginal rate of technical substitution, MRTS, is alpha over beta multiplied by K times L. Okay. You can use this formula. Marginal rate of technical substitution is alpha over beta multiplied by K times L. So if we look at our production function, it's Q equals L to the power 0.6 K to the power 0.4. Okay. So our alpha in this case, alpha, basically the exponent for labor is 0.6. Beta, which is the exponent for capital, is 0.4. Okay. Alpha, exponent of labor. Beta is the exponent for capital. Okay. So for marginal rate of technical substitution alpha, you're going to put 0.6 divided by 0.4 multiplied by K over L. 0.6 divided by 0.4, you get 1.5 times K over L. So imagine a rate of technical substitution is just 1.5 K over L. Okay, colleagues. If you do not want to confuse yourself with partial differentiation, you can use this simple one here. Okay, this one is consumer friendly. So just remember here, colleagues, all that I've been solving is the marginal rate of technical substitution. We're just halfway done. Because remember, the cost minimization condition is where MRTS equals the wage rate over the rate of capital. Okay. So we found MRTS, it's 1.5 over KL. So we'll write our equation like this. Just go to the official answer here. Yes. As you can see here. Marginal rate of technical substitution equals wage rate over the rate of capital. The wage rate in the question they gave us 200. The rate of capital 500. All right. So we need to solve, okay, for K and L. All right. We need to solve for K and L. Okay, so you're going to start it like this. You're going to say 1.5 K over L equals 200 over 500. Okay, so you can get rid of these zeros. You remain with 2 over 5. You cross multiply. You're going to say 5 times 1.5. You're going to get 7.5K equals 2 times L. You get 2L. Okay, so once you have remained with this, find the value for K, find the value for L. Okay, so we can start with K. Okay, if we make K the subject of the formula, you say 7.5 K equals 2L. We want K the subject of the formula, so you divide both sides by 7.5. 7.5 here, 7.5 here. 2 divided by 7.5 0.267 L. 0.267 L. Okay. I'll interpret this, don't worry. Let me just find the value of also L. Okay. Let's also make L the subject of the formula here. So you start again, 7.5 K equals 2L. Want to make L the subject of the formula, so divide both sides by 2. Okay, so you're going to say 7.5 divided by 2. you get 3.75k. 3.75k. Okay, these two things that we've tabulated here, these are what we call the optimal ratios. Okay, k equals, let me even just go to the typed information here. The optimal ratio for labor, or the labor to capital ratio, have you seen L equals 3.75k, right? So what this ratio is telling us is that if you bring in 1 unit of capital, 1 unit of capital, so substitute k for 1. So 1 unit of capital, where we're saying k equals 1. So here you're going to say L equals 3.75 times 1, you get 3.75. Okay. So for each unit of capital, you need to trade off with 3.75 workers. Okay, colleagues? For 1 unit of capital, or what you can think of it as 1 unit of capital is equivalent to 3.75 workers for this frame. Okay. So if you want to bring in 1 unit of capital, you can get rid of 3.75 workers, which we can just round off to 4 workers. This is what this optimal ratio is telling us. Okay. This is the optimal ratio for labor. Okay. Optimal ratio for capital. Okay, here. Okay, where we said k equals 0.26L. Okay. So what this is saying is if you bring in 1 unit of labor, when you say L equals 1, you substitute it into this function here. So you're going to say k equals 0.26. L equals 1. You get 0.26. Okay. So for 1 worker, the frame uses 0.26 units of capital. Okay. Or if you want to bring in 1 worker, you need to get rid of 0.26 units of capital. That's what the optimal ratios are. Okay, colleagues. So let me just recap the step-by-step process of what happened here. Okay, step 1, you get we are using the cost minimization condition to find the optimal ratios of labor and capital. So step 1, get your MRTS, marginal rate of technical substitution. Okay, you need to get that as we tabulated here. That was this 1.5k over L. That is step 1. Get your marginal rate of substitution. Step 2, equate marginal rate of substitution to the wage rate and rate of capital. Okay, so that you can get the optimal ratios for L and K. Okay, so when you equate these two, MRTS equals W over R, the next thing what you need to solve for is make K the subject of the formula and L the subject of the formula. Those are your optimal ratios. Okay, and they'll tell you for how many units of labor you bring in, how many units of capital are being used or can be traded off, and also for every unit of capital that you bring in, how many workers use it or can be traded off with it. Any questions?